So it's my pleasure to invite Professor Kalyan Chakraborty, the first resource person of the day and of the webinar. And as I mentioned in the welcome speech, he gave me all the help in selecting the resource person, and we have a very good, eminent people for this national webinar. I'm really proud, sir. We are all are really proud because of your help and support. We could organize it very nicely. We started this very nicely, and we will do it. Okay, and about just let me give a brief introduction. That is not required, even though for a formality I do that. Professor Kalyan Chakraborty, he is the professor at Harishchandra Research Institute, Allahabad, and he is the director of KSOM, Calicut, and he works in various areas of pure mathematics, especially number theory, cryptography, and in number theory, algebraic number theory, automatic forms, special forms, Lafontaine equations, elliptic, so many areas are there where he contributed a lot. And he has a long list of journey as a researcher, academician, and at various places in the world. He has postdoctoral experience. His PhD is from HRI, Allahabad. Formerly, it was MRI at that time. So he has postdoctoral experience at IMSC, Chennai, Queen's University, Canada, and HRI, Allahabad also. And visiting professor at University of Paris, Tokyo, Metropolitan University, Waseda University, Tokyo, Shandong University, China. A long list I have. So your experience is that much. So we shall utilize it, sir. You. Tribhuvan University, Kathmandu, Kathmandu University, Nepal, Roma Terre University, Italy, Tuos Laurent University, Budapest, University of Hong Kong, Kinki University, Japan, Kyoto Sangyo University, Japan, Northwest University, Xi'an, Shandong University, University of Calgary, Canada, Queen's University again, Laval University, Canada, so many, I think more. And he has more than 100 publications in as the articles in journals, three books or more. I could see three of his books, and book chapters and repository works are there. And reviewer for AMS, American Mathematical Society series, as mentor, as DST Inspire Camp, referee of various reputed journals, chief organizer of the International Conference of Class Groups of Number Fields and related topics, ICCGN FRA. It's a yearly international conference, and he is one of the chief organizers of that program. And today, his topic is on certain integer partitions, and partition functions is an area where Ramanujan contributed very much to the mathematical society. So, sir, with these few words, let me thank you, sir, for all your support once again, and let me invite you to the academic session.
So thank you so much, Dr. Preeti, and it's a really wonderful, it's a real pleasure to be here presenting in this 3-day national webinars on India mathematics and Srinivas Ramanujan. And thank you so much, ma'am, for such an elaborate introduction of mine. Not that, is there, but it's really, it will be a real pleasure. This is the beginning, as I told you. It is really not the beginning, because as you remember that we had, selected all these candidates for our integrated MSc PhD program, and you were such a pillar of strength for us throughout those 2 days. And not only those 2 days, I mean, even after that, I know we are getting all kinds of assistance from your department and University of Calicut for all the required arrangements that need to be made or being made. So thank you so much for your support, and I'm sure that we will collaborate more into this kind of advanced programs. And I'm thankful to my friends, Professor Srinivas, Professor Shanta, Professor Anandavardhana, for really agreeing for this for this particular 3-day national webinars, and we are always there, ma'am. I mean, the development of mathematics in Calicut, as Professor Jairaj has pointed out, will be the priority in my mind. And whichever way, Kerala School of Mathematics, and I have a long list of my friends all over India, not only India, many places in the world, who will be very eager to join hands. Thank you so much.
Thank you, sir. Thank you.
Yeah, so let me begin. So the title of my talk today is on certain integer partitions. As Dr. Preeti, Professor Jairaj has pointed out, that Srinivasa Ramanujan has contributed in many areas in mathematics, pure mathematics, especially in number theory, which has, as an untrained mathematician is remarkable. Why I'm saying remarkable? Because all his, the work is even now after so many years are being so relevant, and people are finding more and more connections in various branches of mathematics, not only in mathematics, in physics, in other branches of science. The relevance of the work that Ramanujan has done long back in his short span of life. So this is one area where Ramanujan has contributed tremendously, and all those results are so surprising. So I chose this is one of my, I'll be giving 2 lectures, so this is the first one. So I chose this particular topic on integer partitions, and which will be in some sense a flavor of the kind of at least few of Ramanujan's works will come, and we have tried to do something similar for other kind of partitions. So that's what I thought, that this will be very relevant for this particular webinar series that we are having. So this is a joint work. So I'll be mainly talking about 2 recent works that I have with my postdoc at Harishchandra Research Institute, Dr. Chiranjit Ray, who is an expert in this area. His mentor, Professor Rupam Burman, is one of the experts in India whose works are being recognized all over for in this area for their contribution. So Chiranjit Ray is the student of Dr. Rupam Burman, and he has also done very good work. So this is 2 works that I'll be, first work I'll touch upon a little more, and the second work, which is just recently been accepted, will be just touched upon. Okay, so this is an outline of my presentation today. And before I really begin, again, I would like to thank Dr. Chiranjit Ray for really helping me preparing these slides, and really thankful to you. Maybe you are there. So the outline of the talk will be some, start with some the definitions of partitions, some examples, some properties of these integer partitions, which is classical one, and then talk about some problems which are yet to be resolved. Then go into, as I told you, these partition functions are being coming up, or the work of Ramanujan are being connected to various areas of mathematics. This is one area, this modular forms. So I'll go into a little bit of modular forms and show you the connection of this partition functions with modular forms. Then I'll go into what are called L regular over partitions. And here the work will be there that we have recently completed. So again, go through slowly because I have enough time. And then the second work that I was talking about, which is called max related integer partitions. This I will just give a brief. That's the target today. And I might be over before my scheduled time. So apologies in the beginning itself for that. So what is a partition? Partition, all of us know. I mean, just by the word itself, it's very clear that what is the definition of a partition. So a partition of a positive integer n, I mean, you can take it for any integer, make the partition 0 for negative integers. So, right, so the negative integers are not into the context here. So it's a positive integer n is a non-increasing sequence of positive integers whose non-increasing. So it's just it's reducing whose sum is n. And this function, suppose given an integer, positive integer n, the total number of partitions of this particular n, the way you will be able to write, the number of ways you will be able to write as a sum of non-increasing sequence of positive integers is this function. So the input is the set of positive integers, and the output is the number of times the number of ways you can write n as a sum of non-increasing sequence of positive integers. That's the output. For example, if you take 5, you can see you can write 5 as 5 itself, 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, and 2 plus 3 ones and 5 ones. So there are 1, 2, 3, 4, 5, 6, 7. So the P of 5 is 7. Okay, so the output is 7. And as I told you that for our conventional, the convention is that we take P of 0 is 1. And if you want to extend it to the whole set of integers, take the partition for negative integers as 0. Okay, so this is an example, and each of these parts are called the parts. The positive integers in a partition, this is one partition, this is one partition. So each of them is called a part, called parts of that particular partition. Okay, so this is starting with an integer. We give a function from that integer to integers, and this is the definition of an integer partition. So this is the function which is the topic today to talk about, and this function has been studied for a long time, as you will see, and still it's a very active area of research. So P of 1 is 1, P of 2 is 2, P of 3 is 3, P of 4 is 5, and you saw that P of 5 is 7. So go ahead and you can see how it increases. So here you see P of 105, not a very big number, but already you can see the number of partitions here. Okay, so so the questions here. So before I move into the next slide, let me talk about what are the problems that one is interested in for these kind of functions, partition functions. So one of the things is proving identities. Proving identities means, let me explain that what is the meaning of that. So you have two sets, A and B, of different objects. Let's say A has different objects, B has different objects, but you want to show the cardinality is same, the number of elements are same. So what are the ways? There are two ways. One is just count the number of elements in A, count the number of elements in B, and you show that they're equal. And so that is what is called the generating function method. And then there is another method, give a bijection from the set A to the set B. So these are the two ways. One is called the generating function ways, and another one is called the bijection method. And if you want to contrast this one with some particular problem, like in a cinema hall, let's say you have number of seats, number of people are there, and you want to see whether the number of seats are equal to the number of people. There are two ways you can do it. Is count the number of people and count the number of seats and show that they're equal. Or another way is to ask all the people to sit down and just see whether any person is left over or any seat is left over, which is called the bijection one. So this is these are the two ways that the identities are being shown. And of course, there is a popular way of what is called the Fourier's diagram. And this diagram depicts this partition of an integer n. And that is also sometimes helpful to check whether certain identities are true. For example, let's see that you want to say that find the number of partitions of an integer n with largest part is k. Okay, so then you want to show, it can be shown that that is equal to the number of partitions of n with k parts. And that you can show very easily by drawing the Fourier's diagram, that you start with the partitions, create boxes for each partitions, and you will see the number of rows, number of columns will be the same. It's very nice, this Fourier's diagram. But not always you can do everything by showing that one. There is sometimes the generating function method is easier and the bijection method is difficult. Sometimes the bijection method is easier, the other one is difficult. Sometimes both are difficult. So people keep trying to prove certain identities like this. Like, for example, you want to show that the number of partitions of an integer n with distinct parts, which can be shown that it is equal to the number of partitions of an integer n with odd parts. So these are the identities that one would like. Ramanujan has proved quite a few identities called Roger Ramanujan identities. So like, he proved one of the identities is like that number of partitions of n, where no part is congruent to 1 or 4 mod 5. And that could be shown as that there's no repetitive or no consecutive parts are there. So these are some of the identities, many of them Ramanujan has proved. And these are very, very interesting, sometimes most of the times by giving generating functions. We'll come to that, a couple of them. So this is one problem. And another problem, as you can see, how is the growth of this function? Can one give asymptotic growth of this function Pn? As you can see how it is growing. So that has a lot of research had gone in Ramanujan. So finally, I think in the beginning of 20th century, with a lot of previous work, so this question was settled by the work of Ramanujan, Hardy, and Rademacher. And the result is here, that you can see that the function is asymptotic. There is an explicit expression which involves some certain 24th root of unity. I'm not going into that one, but approximately, if you take the first term of that particular expression, which Hardy, Ramanujan, and Rademacher has, is like 1/4n square root of 3, exponential pi is here, square root of 2n over 3 as n tends to infinity. You can see graphically, you can see how it grows. So it has a sub-exponential growth, this Pn. Sub-exponential means it is over polynomial but below exponential. Is a proper definition, not going into that. So you can see, so this question really haunted people for some time, and then finally the work of Ramanujan, Hardy, and Rademacher resolved this problem, and it is that expression is really finite, explicit, which they gave. Okay, so this is, I think the history, the Euler is the first person to really study these partitions. And it started from in 1740 when Noidel raised a number of questions to a letter, one of his letters to Euler. One of his questions is how many ways can a positive integer n be represented as a sum of positive integers? Okay, so generating function. So this is like, here, so that means we want to have a product expansion, like here Pn is the coefficient, and mod of q is strictly less than 1. So it is Pn q power n. Euler proved that this is equal to actually n equals to 1 to infinity 1 by 1 minus q power n. As you can see, this is a very familiar, you expand it a little bit. This is geometric series, as you can see, 1 by 1 over q, 1 minus q, 1 minus q square, 1 minus q cube. And this is the series here. And you write this one and then keep collecting the coefficients. So you can write q as 1, so 1 times n1, 2 times n2, 3 times n3. And suppose your n is like this, 1 times n1, 2 times n2, plus up to k times nk. Then here, this ni denotes the number of times I appears in a particular partition of n. Like you can see just in the example, so 3 plus 2, 5, 5 plus 8. You can see here that 3 appears 1 time. So this is like 3, 1 time. 1 appears 2 times. It's like 1 appears 2 times. And 1 appears 3 times. So this is another way of expressing partition also. Okay, so this is how this Euler got this identity here got this generating function for these partition functions. And this is a beautiful result, as if you look at it a little bit, and you will see that suppose you want the coefficient of q3, q power 3, q power 4, q power 5, collect the various ways you can take from here, from there, from others, and then you will get the partition related to that particular number. Okay. So now I can, after that thing, so before I go, there is another, so this problem was resolved, the generating function was done, and the asymptotic growth was also resolved. But still there is a question which is, after a lot of work, people haven't yet come into that. What's called the parity question. That can you give an algorithm? Can you give a way to check when the partition, the number of partitions of an integer will be even or when it is odd? Okay, so this is still work is on, and it's not yet completely resolved. And this shows that, some kind of, so this is another thing that people study, these congruences, which Ramanujan started. These are the famous 3 congruences which Ramanujan got, that he announced in 1919, that he found 3 simple congruences. Look at the beautiful congruences. That P of 5n plus 4, take the n is 5n plus 4, n is of this type, and which is always congruent to 0 mod 5. 5 will always divide that. 7 will always divide that. And 11 will always divide this 11n plus 6 type of numbers, if it is there. So you should note here that only these 3 primes that he got it, not for 3 even, not beyond 11. So 5, 7, and 11, and remarkably, so he proved these first two congruences by really producing the Q series identities. So this is the generating function he produced for these two, for this 5n plus 4 and 7n plus 5. So he gave these two generating functions and proved this congruence. And he remarked, so that's remarkable, he remarked that no simple congruences for Pn will exist other primes than 5, 7, and 11. Look at that, the vision of that person, that he did some calculation, he proved the congruences for 5 and 7, 11 was proved later. And he said that no more primes, no more congruences you will get, simple congruences like that for any other prime. So this already shows the genius that Ramanujan was. And look at that, in 2003, it was proved that Parity Conjecture, result of Boylan and Algren, which appeared in Invention in Mathematics in 2003. Look at the result, what he was really conjecturing, that if L is a prime, and let's say beta is between 0 and L is an integer, this is the congruence what he was taking, which is congruent to 0 mod L. This L and B, these are the only possibilities. As you can see, it is 5, 7, and 11, and 4, 5, and 6. So this was the conjecture he made. He proved the first two. He conjectured the third one, and the conjecture was that no more such simple congruences will exist for any other primes other than 5, 7, and 11. Just think how a person, these are not easy calculations at all, and you are giving congruence for all such numbers. And he conjectured that no other primes. I find it, remarkable. So now there are other congruences also. It may not be possible for that particular simple congruences as Ramanujan was talking about, but there could be other congruences which is quite different from what identified by Ramanujan. In 1916, Atkin and O'Brien, so look at here, it's different from 11 to the power 3 into 13n is plus 237. They proved that this is always congruent to 0 mod 13. So this is a fascinating area of finding congruences for certain types of numbers related to the partition function related to those particular numbers. So in this context, there is a conjecture of Irdos, which says that if n is a prime, this is still a conjecture, then there is at least one non-negative integer nm, depending on this m, which is a prime. Always there exists a non-negative integer nm for which p of nm is congruent to 0 mod m. This is a much bigger conjecture, and for some cases one can, because P2 is 2 as we have checked, P3 is 3, so this is proved for m equals to 2 and 3. Ramanujan congruence shows that it is proved for m7 and 11, and Atkin and O'Brien's proved that it is true for m equals to 13. Okay, so but it's only for these that is known. Okay, so that is congruences, and there is another type is what is called the distribution of the partition functions. So it's natural to consider the general distribution of the partition function modulo some positive integer m. So in 2000, Ken Ono made a significant contribution in this direction, and that's a seminal paper. As you can see, it is in Annals of Mathematics, distribution of the partition functions modulo an integer m. So what he did, he developed aspects of periodic theory of half-integral weight modular forms. Don't worry too much if you don't know. It's just the information that I'm giving. We'll come to modular forms a little later. So used this to prove that there exist infinite families of partition congruences modulo every prime L bigger than equal to 5. So he could prove such a result. Sorry. And but it's all bigger than equal to 5. What about 3? So nothing much is known. So bigger than equal to 5, all primes, he has proved that one, but not for 3. Now there is this parity conjecture as I was talking about, that when it is even the partition function, when it is odd. So there is a conjecture of Parkinson's and Sachs. So this is still a conjecture. And so suppose, what is the conjecture? m is a positive integer, take any r, which is 0 to m minus 1, and then define this, what is called the density, some form of density, that del r mx. Del r mx is simply count the number of n up to x, just below x, so that Pn is congruent to R mod m. So Pn is congruent to R mod m. R is this thing that you have chosen. R could be 0 also. And divide by the number of that number that you have chosen, that del R mx, divide by x. And so this is a well-known conjecture, and that is still a conjecture. It predicts that the Pn, it's evenly distributed modular 2. So this is the conjecture that they proposed, that in 1967, it's Matcom CTO, that if R is in 0, 1, modular 2, then limit as extends to infinity plus infinity, this is half, so evenly distributed. Little is known about this conjecture, but Ken Ono, in that particular work that I had alluded before, is show that it is always bigger than 0. Delta 0 only is always bigger than 0. It's always positive. So it's just a positive being shown, but it says that exactly half. And so still we are continuing with the distribution of other kind of partition functions. Those were the general partition functions, and we will come into some other types of. So this Basil Gordon for fixed integer k, and Ken Ono in 1997, they proved that the number of partitions of n into distinct parts. So you can easily prove that the number of partitions of n into distinct parts is actually equal to the number of partitions of n into odd parts. But let's look at what they proved, that distinct parts. Remember in the 7th partition I showed, there were repetitions, but here it's only the distinct parts that one needs those number of partitions. Is divisible by 2 to the power k for almost all n. So that's a terrific result. That that is PDND for distinct. Because the number of partitions of n into distinct parts, then this is always 1. Almost always it is true that it will be divisible by some power of 2. It's even. You can check in you can easily check for some small numbers, and you will see that the number, if you keep it that you are counting only those partitions which are having distinct parts, it will be always even. I mean, at least you can check few of them. So that's what they proved. Almost always it is even. And Catherine Greenman and Lovejoy, they showed that this is also true for the number of over partitions. I'll come to what are called over partitions a little later. Okay, so this is also about over partitions. We will come. So these are some of the works recently that has come out. So different kind of partitions. We will come into that. So let's go into modular forms a little bit, which will be used in the sequel later. So gamma n, I'm sure all of you know, might be that it's a subgroup of SL2Z, which is like this: 1001 modulo n is an integer, and gamma naught n where c is congruent to 0 mod n, and gamma 1 n is when a and d are congruent to 1 mod n. And n is a positive integer. A subgroup is called a congruent subgroup if gamma n, and this is called for some n. We'll come to that. So if gamma n is contained in gamma, gamma is your SL2G. So what is the definition of a modular form? You take a congruent subgroup of SL2G, one of this which contains gamma n of level n. So what is a modular form? A modular form is a holomorphic function on the upper half plane. Upper half plane means you just remove that x-axis and take the up one where the imaginary part of z is strictly bigger than 0. So take those complex numbers which imaginary part is bigger than 0. So it's a holomorphic. This is called the upper half plane, and so it's a holomorphic function. And we are talking about only integral weight. Some L will come here, as you can see the transformation property that L will appear here. This is called the weight of this modular form. And with respect to this congruent subgroup gamma, if it satisfies this transformation property, this SL2G acts transitively on the upper plane. It's called a the Mobius transformation. All of you know. So Z goes to AZ plus B by CZ plus D. You want to see how this function F, when you just tweak that Z by this transformation, Mobius transformation, how does it behave? So it behaves in this way, Cz plus d to the power L. This particular L, we are talking only about integer right now, and it becomes f of z, it comes back there. So this is called the modularity kind of condition. And then one defines the slash operator, which is just negate that one, minus L f of gamma z, so just other way around, and it has a Fourier expansion. So these are called the Fourier coefficient A gamma n and Qn. So this here Qn is not that Q previously, it is e power 2 pi I z Q, and this n will be coming in the denominator of the exponent of E. Okay, so this has a nice Fourier expansion. These coefficients are very, very interesting. And so this is there's no negative term here, starts from 0. And if it starts from 1, then it's called a cusp form. And because it vanishes at the cusps. Cusps are the, for each subgroup, there are a set of rational numbers which are called cusps, not going into that part, which is a finite set. So this is a modular form, a nice function on the upper plane, which behaves in a very nice way. It has lots of symmetries, very nice way with respect to the natural action of gamma, and it's nice subgroups. It has a Fourier expansion, and the Fourier coefficients are very, very interesting. And they form a finite dimensional complex vector space. In fact, it's a Hilbert space. There is a nice inner product is there. You have nice operators operating on that one. There's a very concrete formula for the calculating the dimension of these functions, and you can write down the generators, etc. So next is Eta Quotient, which we'll be using. The decaying Eta function is defined like this. Here Q is e power exponential e power 2 pi I z. So that generating function for partition function Q is not this one. Q to the power 1 over 24, 1 minus Q to the power n. So Ramanujan did work with this kind of. So a function f is called an Eta Quotient. So Eta Quotient will be coming up. So if f of z is of this form, so f of z is eta is this eta, delta z, instead of z, there is delta z, and exponent it is r delta. What is this delta? Delta is dividing n, okay, for an integer n, positive integer, and this exponent is also an integer. Remember this will keep coming again and again. So this is called an Eta Quotient. We'll come to in a practical application of this one. So what about the modularity? I mean, it looks like there is, if you can show that this is somewhat like behaves in some cases like a modular form, then you will be able to derive a lot of properties through this property that it is a modular form. So this is the modularity of this theorem of Gordon, Hughes, Newman. It's a couple of theorems together we have written here. The Gozart. So suppose f is a Eta quotient, that we have just defined, such that your L, so whenever you talk about a modular form, you have to give what is the weight of that modular form, what is the level of the modular form, what kind of congruent subgroups with respect to which it is a modular form, and how does it behave in the with respect to the cusps, at the cusps. So if you take L equal to half R delta, this is R delta, delta is, take this one. So this is an integer. Suppose this is an integer, that means 2 divides this, sum of the divisors of n. Delta R delta. So delta is the divisor and R delta is that integer, that is the power we have taken. So delta R delta is divisible by 24, and n over delta R delta is also divisible by 24. Then suppose this happens with respect to this R delta and the delta that you have here in the Eta quotient, then f satisfies this modularity condition. So f of az plus b by cz plus d, we have this, some character comes up here, and cz plus d to the power L, f of z, just exactly like what we have seen for modular forms. And here this character is a Jacobi symbol that, that one can calculate here. So it specifically gives what is the character it will come from, and it talks about the weight also, what is the weight, and the next one will be telling you which level it will be coming there. So this theorem will be approached again and again. A particular Eta quotient will come up, we'll check out this L, we'll check these conditions, and then we'll have the character and the weight of the the particular modular form that you would like to show that it's a modular form, you can calculate the weight and the character from here, and the level will be coming from the other here. So the order of the vanishing also is given here because it's a combination of 2, 3 theorems together. So so the order of vanishing of F at this particular cusp is this. Okay, so where it's exactly given what is this CDN and how this CD could be. Because these are the things that will be utilized. The order of the vanishing, we would like to show that it is positive. Then as I told you that there are nice operators called Hecke operators in the space of the Hilbert space of this modular forms. So these are so suppose this is a modular form of level n and weight k, weight L, and the character chi. This is called the Niventipus. Then the action of the Hecke operator is defined by this. F of z, we have an. So what happens to an? An becomes a chi of d power L minus 1, a of nm by d square, d power m. So this operator operates on F, which has this expression like this. So after operating, an becomes this. In particular, if your m is prime, that m, what we have taken here is a prime number, then it has a very nice expression. This becomes a of pn, a of n already we know, the p goes inside, plus chi of p to the power L minus 1, a of n over p. And remember that this is always integer, so p, only those p will appear here which divides n. So it's called a Hecke eigenform. This particular modular form is called a Hecke eigenform if it is eigenform with respect to all the m's bigger than equal to 2, and so this is the eigenvector which comes up. So if it behaves like that, then we will say that this is a Hecke eigenform. So let me come to the work. So this is all the pretext that I was preparing for the work that to explain to you a bit that the current work that I did with Dr. Chiranjit Rai. So usual partition, we have seen it. So there's something called L regular over partition. So we'll come to that. First, what is the over partition? An over partition of N is a partition which was introduced by Cortile and Lovejoy in this particular paper, Transaction of American Math Society. An over partition of N is a partition of N in which the first occurrence of a number may be overlined. So what is that? For example, if you take the over partition of 4, that is 14. So how is that? So it is 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1. This is the usual partition. Then you overline the first occurrence of a number. So you keep on overlining and then you are finished. So you can count that there are 14 of them. So this is another object which was introduced and it has been taken over after that. And as you will see that this will have connection with modular forms. So this has become a pretty useful object, and lots of mathematicians have studied these over partitions. These are some people who have contributed a lot in this partition function theory. Rogers, I was talking about Rogers, Ramanujan, Identities, McMahon, Gordon, etc. And what is L regular over partition that we will talk about? So it's over partition. L regular over partition is number of over partitions of N with parts not divisible by L. Parts, you know, these are each of the parts not divisible by L. For example, so you have got the over partition of 4. So what is L regular over partition? Here L is 4. So this is A4. I will be denoted by AL bar. So A4, 4 is 12. As you can check that 4, how many parts are there in a partition which is not divisible by 4? You can see that only these 2 will get out. So rest 12 of them. If you want to check 3, how many parts are there where 3 divides and remove them? You'll see it is 10. Similarly for 2, it is 6. From here, it's very easy to check. So this thinks that AL bar will be of our interest. So this recently shown in a paper in Identity proved that the licensing formula for this generating function was for this L regular over partitions, and these people showed that a 3j, the power of 3, got a sort of Ramanujan kind of congruences for this L regular over partitions. 27n plus 18 is always divisible by 3. And then in another recent paper that Ray and Barman, they showed that it's actually the congruence between certain of this L regular over partitions. So for example, their result, if you take p bigger than or equal to 5, and let's say this symbol is -1, -2 over p, then for all positive integers L, and alpha, we have these nice congruences. Okay, so 16 will always divide this 4L over partitions of this number. So it's for any j up to p minus 1. Okay, so this is again some Ramanujan type of congruences for these L regular over partitions. Now, to study this over partitions, what Andrews did in a recent paper, he introduced another combinatorial object called a singular over partition. Okay, so Andrews' singular over partition will be like CKIN. There is a bar there over partition. Number of over partitions of n in which no part is divisible by k. Okay, so that's singular. That's the regular over partition we are talking about. Only parts which are congruent to plus minus 1 mod k may be overlined. So why he introduced this particular combinatorial object? He was trying to get the results, like general results for this over partitions, like what we have for usual regular partitions. So he introduced for example, you can easily check if you take k equals to 3 and I equals to, let's say, 1, and take n equals to 4, you can check that C31 bar 4 is actually equal to 10. It's a simple, kind of fun. People who are, students here can check that, writing down few of them. And he proved certain, so it can be easily checked that 3 regular over partition. I was talking about that it's not divisible by L. So there is a relationship with a regular over partition with this Andrews singular over partition. It's same as 3-1 regular over partition. So take k equals to 3 and I equals to 1. This was same. That is easy to check. And Andrews got certain mod 3 Ramanujan type of congruences for the singular over partitions. So, so he showed that C31, again only 3-1, 9n plus 3 is congruent to 3-1, 9n plus 6 and is 0 mod 3. So modulo 3, he got some nice congruences for this singular over partitions. So this is like 2015. And this Chen, Rischorn, and Sellers, same time they showed that this is always even. C31 bar n. Take any of them, that will be always even. 0 mod 2. And in 2016, Nike and Greece also got for 3-1 only some nice congruences, and they conjectured that 12n plus 11 C31 bar is congruent to 0 mod 144. And that was confirmed by Barman and Ray in that in Ramanujan Journal 2018 paper. This conjecture of Nike and Greece. Okay, so research in number 3, Barman and Ray has another interesting paper which says that C31 bar is almost always divisible by not only by 2, it's 2 power k and 3 power k. So this is the kind of results that was previously done. And what we did into this recent paper, which has appeared in Ramanujan Journal, that if you take L equals to this distinct primes with the exponents are primes bigger than or equal to 5, and if this condition is put, then you can have a density distribution of this L regular over partitions that we can show that almost always it is divisible by pi to the power j, some powers of these pi's. And as a simple corollary from here, one can show that for if you just put 1 prime, take it a p bar n is 0 mod p power k. So this is almost always it happens that it will be divisible by this powers of primes that you have started with. For p bigger than 3, any prime. So let me go through quickly a little bit of idea about the proof, that how proof of this particular result, that how you get it. It is a nice idea. And then maybe I will have to skip a couple of things. So this is a generating function for this L regular over partitions. And here this is the Q shifted factorials notation, that AQ infinity is just 1 minus aq to the power m minus 1, which is very standard in partition theory. So this is a generating function for AL bar n. And if we write AIZ is this, then one can show that it is the eta function, dedicated eta function is coming up here, 24z, and eta 24 pi to the power AIZ, pi here. So this is a quotient of two of these dedicated eta functions. And one can show that AI pi to the power j, which is just, you can calculate from here, and it is, so this is the first thing to show that it is congruent to 1 modulo pi to the power j plus 1. So that's the next step in the proof. And suppose you denote by bijl z, by this, the quotient of these eta functions that you see here. So then the target will be for us that to show that bijl, bijl z, by using that theorem of modularity theorem I was talking about for eta quotient. So this is the eta quotient here, first to check. And then to show that by using that particular theorem, that it's in fact a modular form, calculate the level, the weight, and the character by using those theorems. Okay, so and then one can show that that's the later part, but first one shows that, this is AL bar, the over partition is coming here, and it is congruent to modulo pi to the power j plus 1. So suppose you show that it's a modular form of a weight using those particular thing, then you will have that this A bar Ln is also, you will get the congruence condition there for this particular L regular over partitions. That's the idea. And so this is what the level comes up, 1152L. The gamma naught n we are talking about, the n is this, by using that particular theorem. And it is holomorphic in the cusp. If we calculate the order of the vanishing by that particular theorem, we need to show that this particular expression is bigger than or equal to 0. How do we do that? So we have two cases. This is the first case, and this is the second case. In the first case, it turns out to be this, and this pi to the power ai is always bigger than this. The same what you are seeing here. So this thing is bigger than 0. This thing is also bigger than 0. So we'll have the holomorphic at the cusp for this particular bijl. And that will tell us that, in fact, on the weight part, as I told you, there is a they have given the recipe to calculate the weight, the L, in fact. So the weight is this here. This is the level that comes up, and the character can also be written. Okay, so now we have this nice result that this bijl is in fact a modular form of this weight, this level, and the Leventy-Pass is also can be written down. So how do you get the density result, which we are talking about? This is the result of Sayre, which gives us the density result, which says that it's a very nice result, that if A denotes the subset of integer weight modular forms, A denotes the subset of integer weight modular forms for mk, gamma naught, and chi. Okay, this is what we are in. We know the k, we know the level, we know the Leventy-Pass here. For our bijl, which we need to show, we have shown already that it's a modular form. We calculated the weight, we have calculated the level, and the character also, whose Fourier coefficients are in OK. That means are integers of some number field. And suppose n is in OK is an ideal. So in OK is the ring. So we can talk about the integral ideal that we're talking about. If fz is in A, has a Fourier expansion, so A is a subset of the set of all integer weight modular forms. This A is just a subset here. Suppose this f, which is in this particular subset, has Fourier expansion like this, an q power m. Then there is a constant alpha bigger than 0, such that if you count the number, that n less than or equal to x, so that an is not congruent to 0 modulo this particular ideal. So ideally, when you come down here in the bottom level, it will become an integer. Is big O of x over log x to the power alpha, which is not congruent to 0 modulo m. And we have shown by our previous result that this bijl, it belongs to this here k, here is this pi to the power j, pi to the power ai minus 1 by 2. This is the level, and the chi also can be written, just not written here. So we have proved that one, and then We have also shown that in some, I have not shown it here, but in the paper, if you can find out that it has been shown that Bijlz is this, which is congruent to, modulo, this is this modulo Pi to the power j plus 1. And if you combine this result with this theorem of Serre, we have this density result, which says that almost always we have this divisibility. So this not divisible by Pi to the power j, this limit is 0. Okay, so it's always, almost all the time it happens that this L regular over partition with the conditions that we have n is written in particular form with some restrictions on the exponent of the powers of the primes that it comes up, then that is almost always divisible by Pi to the power j. So this is how the technique of modular form, which is used here to find the distribution of certain this L regular over partitions. And so this is the first result that I wanted to show in front of you, and that how modular forms this particular kind of partition functions, they come up as the Fourier coefficients of certain modular forms. Okay, so this is the first result, and the other result that I want to show you. So this is not just we have produced. So this particular paper contains quite a few results. So that was the first one, and there is another result which I want to give you again a little bit of idea that how it goes through. So it says that so this is an infinite family of congruences. That's also another problem that people take up. That can you show that yes, there exists family which is which contains infinitely many partitions, which has this congruence property, all of them. Okay, so let's k and n be non-negative integers, and for each I, we choose with here between 1 and k plus 1. The PIs are the prime numbers such that they are all 3 mod 4. Okay. Then for any source, only 3 mod 4. For any integer j which is not 0 mod pk plus 1, any of these primes that you have chosen, then this A5 bar, so it's only for 5 bar, is congruent to 0 mod 8, always. And you can keep adding that one, so you'll get an infinite family of members. So for example, if you try to simplify the situation, let's take P1, P2, Pk plus 1 is all just P. So then from here, what we get that A5 bar is 4P to the power 2K plus 1. This is far more simplified, is congruent to 0 mod 8. 8 will always divide this kind of over partitions, L regular over 5 regular over partitions. Whenever j is here, the j is not congruent to 0 mod p. So j should be different from p should not be a prime factor. In particular, if you want to reduce more, let's take p equals to 7 and take any j which is not 0 mod 7. Then you have this nice congruence. That A5 bar, and if you put up the values here, you'll see it's 196n. It turns out this one turns out to be 28j plus 49 is 0 modulo 8. Take any j which is not a multiple of 7, put it here, and you will have this nice congruence. Okay, so this result talks about that. And again, let me give a brief how this can be proven. So this is the generating function of this L regular, 5 regular, in particular it is 5. So it is A5 bar n, q power n. So this is the q-shifted factorial notation that is here. That's well known. And so there's a dissection formula which Rischon and Sellers, they gave for this this q5, q5 and qq. So you can see that it can be split into 2 parts. And then use this one, that A5 bar n here, and then one can easily write that this particular expression as sum of 2 of them. Okay, and then for further simplification, when you do is A5 bar to n plus 1, one can show that this is 2 times this particular expression comes up here. Remember, we need to show 0 mod 8, that A5 bar n with certain, n looks like a particular form. Now, this is a result of Ramanujan, which gives a dissection of this particular 1 by q4 infinity, which was collected by Bushbund in one of those Ramanujan's collected works. So we use this one. in A5 bar that the previous one, and we get that this is congruent to 0 mod 8. So this A5 bar 4n plus 1 q power n, plug in here Ramanujan's results, so 2 q infinity, q power 5 infinity modulo 8. And now this A5 bar 4n plus 1 q to the power 4n plus 1, one can check easily that it is twice that eta dedicated eta function comes up here. And by using the same result that I quoted before, one can check the level, one can check the weight, and the character that comes up here for this eta 4z and eta 20z, and one can show that it's the weight comes out to be 1, and the level is 80, and the character is minus 20 over d. And it's also true that it's a Hecke eigenform. And if you expand that one, eta 4z, eta 20z is like q power 5, q power 9. So this is an q power n form can be written. So this is the Fourier expansion. It comes up. And note that if an is 0, if n is not equal to 1 mod 4, not congruent to 1 mod 4, and A5 bar 4n plus 1 is 2a 4n plus 1 modulo 8. So that will be used in the later part. And this is also Hecke eigenform, and this if you take the operators TP and then it transforms like this, because P is a prime here, just follow that formula of the Hecke eigenform, and it turns out that the ANs become this APN, and this is the general formula, and then it's a Hecke eigenform, so some eigenvector will come out AN q power n. So this one APN is equal to lambda p times AN if you compare the coefficients. And A1 is 1, it's a normalized form, and A1 by P is 0. Putting n equals to 1, we can check that is AP is equal to lambda P. So Pth coefficient is simply the Pth eigenvector. So this is 0 whenever for all P which is equal to 3 mod 4. Whenever it is not equal to, so it is not equal to 3 mod 4, we'll have, because this lambda P is 0. And then we check two cases where P is dividing, not dividing n, and P is dividing n. One is to do a little bit of calculation to really arrive onto this particular result, that A5 bar 4p square n plus p square PR 1 minus p square is 0 mod 8 when P does not divide n from the above expression. And when P divides n, it is A5 bar 4p1 square plus the product pk square n p1 square up to pk square. So this is minus 1 minus 20 by p. Remember, this is the level, this is the character, comes up to the power k, and A5 bar 4n plus 1 mod 8. A little bit of work is there to get this particular form. So from these two expressions, we have to do a little more analysis, study this, how this characters, if you vary your p, what kind of residues that it will be varying, because you are in a progression, and then one can arrive onto the result that I was quoting, that A5 bar, this is the 5 regular over partition, and so this particular P1, P2, Pk that we have chosen it, so it's a general form, so we get an infinite family of congruences. If you keep varying your P1s, you'll get a partitions, infinitely many partitions, which will have, if you give those conditions satisfied, then they will be all satisfying this particular nice congruence that is congruent to 0 mod 8. So I wanted to emphasize on these two results. These contain some more results in this particular paper to show you that there is a very close connection between certain partitions and theory of modular forms. And using theory of modular forms, the arithmetic of the results of theory of in modular form is quite rich in classical modular form and over other forms also. So that can be utilized to get nice arithmetic properties of certain partition functions. And as I tell you that these partition functions are combinatorial objects, and they crop up in many studies, many other different subjects they crop up. And if you can get nice congruences, the divisibility, the parity, and how their density, how their varying distributions, then that will be quite useful to study. Like if anybody is interested, Ken Ono has done many works relating these partition functions to various objects like, class numbers, and even I remember there was a in black hole and other things. So these partition functions are very important, and of late it is seeing a lots of activity because of its relation in various areas that it is coming up. So this paper contains some more results. This is one of them, which I'm not going into any kind of brief proof or so. So what is this saying? This is called a multiplicative formula. So k be a positive integer, and p is a prime number such that p is 3 mod 4, just like the previous. This result almost comes from the previous explanation that I gave. And let R be a non-negative integer such that p divides 4r plus 3. So 4r plus 3 is congruent to 0 mod 3. 4r plus 3. So this is 4r plus 3, as you see. And then in that particular case, A5 bar, this 5 regular over partition of this 4p to the power k plus 1n plus p into 4r plus 3 is congruent to this function fp. Fp is -1, so it is either -1 or 1. -1 if p is 3 or 7 mod 20, and it is 1 if p is 11 and 19 modulo 20. So it's +1 or -1. A5 bar, so there is a so this minus this will be divisible by 8, 0 mod 8. So it's A5 bar 4 p to the power k minus 1 n plus 4r plus 3 by 5 by p is modulo 8. These two are same. So this is kind of a multiplicative formula. So there are a few more results in that particular paper, and let's give a full stop here in this particular paper. People who are interested can have a look into this. This is now online, and I think it has appeared also. Okay, so this is about the first paper that I wanted to talk about. It, and then this is this next paper that as I told you that I'm not going into any of the proofs and all, but you can see this is something related to MEX. So MEX function comes up at many places. So there's a little story behind this particular paper. So to commemorate Ramanujan, to remember Ramanujan, so that's why I have decided to put in here this Hardy Ramanujan Journal. People might know about this journal. So this is a journal dedicated to the kind of work that Ramanujan did, and it is a prestigious journal to us at least. So Hardy Ramanujan Journal decided that they will come up with 2 issues dedicated to the fond memories of Srinivasa Ramanujan. So I got an email from Professor Bushband and Professor Atul Dixit in IIT Gandhinagar that they are coming up with these 2 issues. So it will be nice if I can contribute in one of those issues. So I talked to Dr. Chiranjit Ray that will it be possible, because there are other areas that I work, but it will be very nice if you can get some nice result related to partitions, and we can submit to see if that can be published there in that particular issue, one of the 2 issues. So I'm happy to say that that came up, and it will be appearing in one of the 2 issues that will come up soon. The paper, I'll come to that one. But what is this next related integer partitions? So these are again combinatorial objects, and it has been used, maybe in 1930s or so it was introduced, and this MEX function, and it has been used many occasions, especially in game theory, in combinatorics, and all. This MEX function is quite a popular one. So what is this relation with partitions? So Frankel and Pelt, this is defined the minimal excludant. So this MEX is sometimes called minimal excludant on a set S of positive integers as the, so what is this function? Excludant or MEX function on a set of positive integers as the least positive integer not in S. This is a gap function also, sometimes it's called. So and best known for the applications in combinatorics and game theory. So see the definition that it's the given a set of positive integers, it is the least positive integer which is not in the set, the least one. That's max of S. And George Andrews and Newman considered the minimal excludent function and applied it to integer partition functions. The minimal excludent of a partition pi, so they defined it, the max function for a partition. So the minimal excludent of a partition pi is the smallest positive integer, like any partition, which is not a part of the partition. Okay. So again, it's the same thing that you have a set of positive integers and you are defining the max function, the minimal excludant, which is not there, the minimal one, which is not there in the set. So it certainly can be defined over a partition, pi. So they took it up in this max function in partitions. And in some literature, the minimal excludant of a partition is also referred to as least gap or smallest gap or pi. So this is the same thing that we are talking about, the smallest gap or the least gap. So Ballantyne and Markov, okay, they got a relationship in this way. So the R gap of a partition pi or the max, so the R gap of a partition pi is the least positive integer that does not appear at least R times as a part of pi. So R is coming up at the R gap. So R times this doesn't come as a part of pi. Well, take a little time and try to understand the definition, and then you'll see that there's very nice connection. The R gap of a partition pi is the least positive integer that does not appear at least R times as a part of pi. Let SR pi be the smallest part of the partition pi appear in less than R times. So SR pi be the smallest part of the partition pi appearing less than R times. And they define what is called the sigma R max n. So R is here, SR pi. So then sigma R max n is simply to collect pi in Pn, SR pi. So this is, okay, so let's see some examples. So all the three gaps in the partition 5 are. So if you take S35, it is 5. So we're looking at 5. So S35, the minimum gap, the first one is 1. 4 plus 1, it is 1. S3, when you take the partition of 5, it is 1. 3 plus 1 is still 1. And here S3, 2 plus 1 is 1. S3, 2 plus, this is 2. And this is 2. So sigma 3 max 5 is 9. So what was sigma 3? So sigma R max n is simply pi over this, the partitions we are taking, P of n. Sometimes P of n it is written, pi of n. So this is among all the partitions of n, and sum over SR pi. So this is what is denoted as sigma R max n. And here's the generating function for that. And if you do the simple calculation, one can check that sigma 3 max 5 is 9, okay, by using the formula. So what they proved, that Franklin and Pale in the idea that sigma 1 max n, if you take your, like R is 1 and max n, that's what, max n is simply the cardinality of D2n. What is D2n? It's a set of partitions of n into distinct parts. We were talking about distinct parts before, using two colors. Okay, using two colors. So you might take, two colors to be 0 and 1. And for 5, you can try to find out what are how many partitions are there using these two colors, 0 and 1. And they showed that sigma 1 max n is the number of partitions. D2n is the set of partitions of n into distinct parts for n using two colors. They got this nice relationship between the sigma 1 max n and the number of distinct partitions of n using two colors, right? So this is a very nice result, that using two colors. And then in 2020, in JNT, Ray and Barman, as I told you that Ray and Barman has done plenty of works in this in these areas. Of course, Rupam works in many other areas, is one of them. So sigma 1 max n, so this is they showed. And again, they talk about the divisibility. So sigma 1 max n is almost always divisible by 2 power k. So again, some density result, they showed that by just the previous result that modulo 2 power k, the sigma 1 max n is almost always, it is divisible by 2 power k for any positive integer. It's a beautiful result. And then they have, Ballantyne and Mark, they got this the relationship with sigma r max n and what are called triangular numbers. The partition of this, n minus r tk. Tk's are the triangular numbers n into n plus 1 by 2. So they showed that sigma r max n is actually this, some kind of recurrence relationship type. So in this recent work that I was alluding before, that which was for this particular issue of Hardy Ramanujan, 2 issues of Hardy Ramanujan Journal that is coming up. This is the result that has is now accepted now. It will appear soon. So what we proved in this particular paper that sigma 2, so it's sigma 1 was there previously, so sigma 2 max n and sigma 3 max n are almost always even. So more generally, we proved that, so it was, if you go back to the previous result, it was sigma 1, which is Ray and Berman is there. Sigma 1 max n is almost always divisible by 2 power k. So this is a nice kind of a generalization of the result for 2 and 3 that we could do. So this is almost, if we take r equals to 2 and 3, it's a 2 and 3. So we could show that this max related this partition function, this sigma r max n, is almost always even. So not only even, it is divisible by 2 power k for any positive integer k. So in other words, that we could prove in this paper that for almost every non-negative integer n lying in an arithmetic progression, the integer sigma r max n is a multiple of 2 power k, where this r belongs to 2 and 3. So, as you see that, because as Dr. Preeti was telling and Professor Jairaj was also telling that, this 3-day webinars that we are having, one of the main aim is to really for the young researchers, the teachers who are working, to look into people who are working in these partition areas, in modular form areas, or general, basic number theory areas, elementary number theory. This is a very rich area. As you can see, there are still a lot of work has to be done. And this is not just a, pure curiosity that one is asking. These kind of partition functions do come up at various areas. So studying their arithmetic, like distribution, like the parity, like the congruences it satisfies, certain identities related to those particular partitions, proving those things are quite important. And it's a very, I think it's quite a fertile area. Like we are talking about only one n. There could be questions where you take up two partitions, two integers n and n. There are generating functions for that one, and one could try to generalize these kind of results for those. And of course, as you see that sigma r max, sigma 2 max n, and sigma 3 max n has already been proved. So even before I told that there are certain results which are not yet known, the parity of the usual, the classical partition function, the ONO type of result, and then using the knowledge in modular forms and other things in the algebraic number theory to get some nice arithmetic properties for the partition functions. So I think that's what is there for me to present today. And thank you so much for your attention. And that is it. I think I am finished here. Thank you so much.
Thank you, sir. Thank you very much for this innovative speech. And this really, it's a part of the pure mathematics. And many people, but not only in number theory, and also algebra, people are also using this kind of techniques. And this equations and inequalities, we are using for their own research. So I think our participants may have some queries regarding the topics.
Yeah, sure, I'm there. That's why I didn't go out of the slides.
Yeah. Okay, then.
Sir, in your work with Rohit, the Journal of Ramanujan, you restricted P greater than or equal to 5 strictly. So is the another part is open or is it already proved?
That Ramanujan Journal paper, the first paper?
Yeah.
Yeah, I think the other part, we see the problem is that you have to really get into a modular form there to try the method is there. So as far as my knowledge goes, I think for 3, it is not been done. And maybe this particular method is not going to work there.
Thank you. Sir, one more question. It is my anxiety. Sir, is that asymptotic that format that P of n in terms of exponential function?
Yeah.
Is it result by Ramanujan or?
Yeah, it's a joint result. Actually, as I was mentioning, that a lot of research was done. So basically, it's a joint work. And together, all the works of Hardy, Ramanujan, and then finally by Rademacher. So that 20th century first half, people were really, so it's a collection of lot of works together. So I've just put it Hardy, Ramanujan, Rademacher. But basically, 3 of them contributed mainly to get that asymptotic formula for Pn.
Thank you, sir.
Thank you so much.
No more questions? Yes.
So I can stop sharing, ma'am.
I have one question.
Yeah, sure. Please.
Yeah, so in that Sayre's result, is it for like arbitrary modular form or like it has to be Hecke eigenform or at least cusp form?
Yeah, that's a good question. I have to look back. It's like MK gamma n. I think. Let me go back.
Yeah.
It's just modular form it talks about. So I have to really check it, and it's a good question. But it looks like pretty general to me. Like integer weight modular forms only talks about MK, not even SK.
Mm-hmm.
So
Okay. Yeah.
I will have to check it.
And I thought about Hecke eigenform because at least if it is without complex multiplication, we could use like Galois representation and Chebotarev. Maybe we could do. But
yeah, maybe possible. But that I'll just check it because it says in MK, but yeah, it looks too general. But I'll get back. Yes, that's a good suggestion that you are giving, that one can use other techniques.
And also here, I think M must be non-trivial ideal.
It's a non-trivial ideal, right?
Yeah, yeah. Mm-hmm.
Right. It should be, yes. I should be more careful. It's a non-trivial ideal.
Yeah. And also, does this constant alpha depends on M?
Then there exists constant alpha that is not very clear to me, but as it turns out to me, I have to really check this result. It should be depending on this particular ideal. So suppose this is an ideal that there exists, then there exists a constant. So modulo M we are talking about. And yeah, the paper also have to go back that what is this particular alpha coming up there. And this is, so this result needs a little more look into it. Yeah, thanks for pointing that out.
Thank you.
Yeah.
Sir, in that Dedekind's eta function, is that 24 or 12 has to do something with this?
Yeah, ma'am. What the 24 that is coming up?
Yeah, in this expression, q to the power 1 by 24.
The 24 is a dedicated eta function. Actually, Ramanujan's that 12 with 12 plus form. It comes up from that particular expressions from there. So maybe it has to do something with that dedicated eta function, the power that is taken. So which okay, so there may be yeah, so 24. Here, the DCP, what you are telling, 24 here.
Yeah, 24 is coming.
Yeah, because I think I have to go back to that particular result of
Connecting that is eta
that Eta Quotient. So I think so that, which is that main theorem.
Yes.
Dedicated eta function here. That's the definition of 1 over 24 because there will be this certain properties to follow. So here that's how that Ramanujan, the tau function, the first form of which 12 comes up there, and the 24 is important there. And what was the result? Key operators.
That may be because of the presence of 24 and 48.
Yeah, the GCT, that particular result of those people who check the modularity, modular forms, the function, and then the key operators. Okay, that result is that result should be somewhere here. I mean, where the calculation of the cusp vanishing and no, not. Yeah, the 24 certainly is important there. And,
regarding the eta function, they are something saying something related to the Leech lattice.
Yeah. So this eta function comes up there. I'm not really much aware of that one, but I know that there is some connection with that eta function and this lattice we're talking about. But where is that result? Strange. Yeah, there are connections certainly for sure. This dedicated eta function comes up in many places. These partitions come up here, and then modular form it comes up there, the first form there. But somehow that particular Eta Quotient and then modular form. Anyways, somehow that particular theorem is, but the 24 is important, and I don't know much about this lattice theory. So this calculation comes from that particular theorem that is somehow, I don't know where it has vanished. Just to check the vanishing of at the cusps. So to conclude really this one that it's a modular form, in fact, that Eta Quotient, this weight and this level and this character, that particular theorem. Yes. Yeah, I'll check that one, ma'am. If there is any connection with Eta Quotient and so-called Leech lattice, might be there.
Okay, sir. Thank you.
Yeah. Yeah, maybe if any other question is there,
Is there any
queries and suggestions.
dear participants? Do you have any comment or? So I think no, sir. So,
So I can.
yes. So, okay, so shall we wind up, sir?
Yeah, I
Yes.
think it's already the time and
Yeah.
lunch time for all this. So
Yes, sir.
so okay, ma'am. So see you again on 24th.
Oh, yes, sir. We have one more session by Professor Kalyan on 24th. Yes. It is on complete solutions of certain Ramanujan type equations.
Yeah, that's another area where Ramanujan has contributed, so I chose that one.
Okay, sir. Fine. Fine.
Okay,
Okay,
thank you
we
so
will
much,
be
ma'am.
back. Thank you.
Yeah,
Thank you all.
bye.
Okay.